Okay, wonderful. Yes, thank you so much for the introduction and for inviting me to join you today at this nice meeting and giving me an opportunity to talk about our work at Columbia University on ultra-cold molecular clocks. Quantum science with small molecules has really flourished in the past decade. It's opened the window on many new research directions, given us insights into fundamental chemical processes, allowed us to simulate very complex quantum materials and design quantum simulation and quantum information protocols. And also opened the door to many experiments in fundamental physics that were not equally possible or equally sensitive with atomic systems. While these directions sound a bit separated, in fact, they face many common challenges. For example, to create quantum simulators and to create fundamental physics sensors such as clocks, we need to conquer some of the same challenges. For example, both for qubits and for clocks, it's extremely important to create long quantum coherence times to keep the system coherence alive for as long as possible. And this is one of the challenges that we face in our work. So here are a few of the questions that we address through the research that I'll discuss today. We would like to understand if small molecules can contribute to our understanding of fundamental forces. And this includes both new undiscovered physics as well as old physics, such as QED, which still plays a critical role in high precision measurements and also in our understanding of atomic and molecular structure. We are exploring whether it's possible to control molecular states across a large range of the electromagnetic spectrum, and also how to decouple the molecular internal dynamics from the environment in order to achieve the most precise quantum control. And finally, we're also investigating whether there is any metrological advantage for using molecular versus atomic systems. And of course, the first task in working with ultra-cold molecules is creating them. And two different pathways can be used to create samples of molecules at microkelvin temperatures. One method is to directly laser cool molecules that have an alkaline earth metal optical cycling center. So these are the metals in group 2 of the periodic table. This metal is typically bound to a halogen, such as fluorine, or possibly to hydrogen. And it's even possible to substitute the halogen or hydrogen with a larger functional group, which can give access to polyatomic molecules. And the second method is to laser cool atoms rather than molecules. And these are usually alkali metals in group 1. And then these ultra-cold atoms are then assembled into diatomic molecules in their ground state using magnetic or optical fields. But alkaline earth metals in group 2 actually have many features that are very attractive for both laser cooling and for metrology. And these features also transfer onto the bound molecules that are composed of these atoms. But on the other hand, these group 2 atoms don't have any unpaired electron spins. And for this reason, they're difficult to control with magnetic fields. We've solved this particular challenge by using all optical methods to create ensembles of diatomic molecules made of strontium atoms. And these molecules are there in their ground state. These are quite unique ultra-cold molecules with purely van der Waals interatomic potentials. So these ultra-cold van der Waals dimers, strontium-2, they have two key features to keep in mind. one important property of these molecules is the existence of very narrow optical transitions that arise. They're of this singlet triplet type or intercombination type that also exists in strontium atoms. And these narrow optical transitions provide a very powerful capability for quantum state control. And also not shown here, there's another series of optical transitions that are super narrow because they're forbidden by the molecular inversion symmetry. And the second important property that I'd like to point out here is the completely spinless molecular ground state for bosonic strontium isotopes. As you can see here, it asymptotes to a pair of atoms in singlet S0 state and no nuclear spin. And this relative simplicity of this ground state potential is an advantage for precise metrology and ab initio calculations. So to illustrate the point about the ground state van der Waals potential, here you see the ab initio calculated potential that's shown with red points, and also the experimental potential. This one's derived from traditional spectroscopy, shown with the blue line, and there's very good agreement at the level of 1%. So as I mentioned earlier, one way to create ultracold molecules is to assemble them from atoms that are laser cooled to microkelvin temperatures using, and the assembly is done using light or a magnetic field. So our strontium dimers are created by optically making excited dimers, which then spontaneously decay to the electronic ground state. And the photons then take away this binding energy such that the resulting molecules are still at a few microkelvin. And then since strontium atoms are non-magnetic, we use only optical techniques to create the molecules. So the molecules are trapped in a one-dimensional optical lattice, which is a standing wave of retroreflected light. So initially, this lattice tightly holds the atoms in the bright microtraps, or we also call them lattice pancakes. And then the molecules are also created in the lattice, which preserves the original microkelvin temperature. And then any probing light that propagates along the lattice in order to strongly suppress Doppler dephasing. So this is the setup that we use to create the strontium molecules by laser cooling an atomic beam that you can see near the top, and then trapping the atoms in an optical lattice and then photoassociating them. So this picture is a bit outdated actually, but now about a dozen laser systems are used to create, trap, and probe the molecules. So the intercombination transition, which is from the singlet to the triplet state, has proven to be really an incredibly useful tool in also imaging the molecules and also for studying quantum state resolved photochemistry. So in this case, the optical transition is from a ground state bound level to the singly excited continuum, as shown on the top left, and potentially back down to the ground state continuum. Continuum is where the molecule is split into its atomic fragments. Then on the bottom left, here's a photodissociation spectrum that's very narrow because the long-lived continuum, the excited continuum, has a very long lifetime. And then the images show the side view of the emerging fragments. But when we image these exploding molecules, not from the side, but by looking into the symmetry axis of the trap, then we observe non-classical angular distributions that clearly show matter-wave interference, as you can see on these calculated and experimental images on the bottom. And this type of interference is really a key feature of ultracold reactions. So the quantum state of the fragmented molecule is determined entirely by the well-known initial quantum state of the molecule and also of the photons that we use to break it up. And by selecting their quantum states, we can control the shapes of these resulting partial waves. We have also used this technique to probe the continuum with a high sensitivity to features like reaction barriers and collisional resonances. So here are a couple of specific examples of quantum interference effects that we see in ultracold photochemistry. So the strontium molecules are dissociated here into their ground state continuum, such that all the outgoing quantum states are completely known, as well as their relative phases. And in both these cases shown here, we are essentially imaging different coherent superpositions of G-wave spherical harmonics. And these result in these 8-fold fragment patterns that you see. So the experimental images in both cases are shown on the top right of each square. And the calculated predictions are illustrated around it in 3 different ways. This very long-lived intercombination threshold also gives rise to a completely new type of super narrow optical transition in these molecules, which is actually absent in atoms. And this is a transition to the state with the same inversion symmetry as the ground state, which is even, or G Gerade. So the transition mechanism is a magnetic dipole, and the strength of this effect is proportional to the bond length of the molecule squared. And these very narrow transitions result in 2 families of excited molecular states, the superradiant, which are still quite long-lived, or about 10 microseconds, but their decay is electric dipole allowed, illustrated on the left, and subradiant with lifetime of order 10 milliseconds, so 1,000 times longer, illustrated on the right. The subradiant states provide a handle for optical control of the molecular quantum states. That's very valuable. So here on the left, we have coherent optical Rabi oscillations. And on the right is a measured lifetime that approaches here 10 milliseconds for a subradiant state. The subradiant and other long-lived excited states in molecules also provide exciting opportunities for metrology that would be interesting to explore in the future. Now, the subradiant states are very useful for working with molecules that are trapped in an optical lattice. So we can take a broad spectra of these states, as you can see on the top, and then we observe the expected red and blue lattice axial sidebands, in addition to the narrow carrier peak in the middle. So these measurements of the axial lattice trap frequency allow us to precisely calibrate polarizability measurements for different molecular states, which is important for coming up with optimal designs for molecular clocks. And also through this, we can calibrate the molecular density for understanding ultracold collisions. Also zooming in on the carrier here on the bottom and measuring its asymmetric width directly yields the temperature of our molecules. And jumping ahead for just a moment, we can also see the lattice sidebands, not just with 1 photon, but as is the case here, with 2 photon Raman transitions. These are up and down transitions that take place between vibrational levels within the electronic ground state of the molecules. In fact, we can hide these sidebands in the so-called clock mode when we use co-propagating Raman laser beams, as you see on the left, or we can reveal strong sidebands in the counter-propagating configuration, as you see on the right. This gives us the flexibility to measure the molecule temperature directly through these sidebands without using narrow atomic transitions, but using the molecules themselves, while on the other hand, we can suppress the sidebands and all the associated line pulling and systematic effects. Okay, so far I described high resolution spectroscopy of the molecules that are weakly bound, which is how they're initially created from the laser-cooled atoms. But to make the best use of the molecular clock, it's important to be able to create the molecules in the absolute ground state. In fact, we can now create ground state strontium-2, which is the first ultra-cold molecule of this type. To do this, we momentarily switch off the lattice. This removes decoherence due to the light shift and results in very narrow EIT signals like the one shown here. This is electromagnetically induced transparency, where the pump and probe coherently connect the highest and lowest states in the molecular potential. And this is the prerequisite to carrying out efficient transfer from the weakly bound or vibrational state to deeply bound vibrational states. So in this free space environment where the lattice trap is switched off, we implement a stir-up or a stimulated Raman adiabatic passage. So initially at low times, polar molecules are in the most weakly bound state, which we call V-1. Then the resonant Raman lasers are smoothly pulsed on and off to transfer the molecules to the ground state, V = 0. Now we cannot see these deeply bound molecules directly, so it looks dark, but we can reverse the stir-up process and recover the molecules again in the weakly bound state. And from the number of these recovered molecules, we deduce that the one-way transfer efficiency is 75% in this trace, and now we actually get over 90%. So this black line is a simulation based on the optical block equations that agrees with data very well. And here is the conceptual implementation of the molecular clock. It involves a pair of vibrational clock states that each see the same trap depth in a so-called magic optical lattice. And these states are coherently coupled to each other using light. Since direct vibrational transitions are strongly forbidden, here we drive a 2-photon or Raman clock transition off resonantly coupling to a long-lived excited molecular state. And here the details of the ground and excited molecular potentials are shown in some more detail. The absolute ground state is bound by approximately 1,000 wave numbers, and both probe lasers in the Raman configuration, as well as the optical lattice light, are phase locked to an optical frequency comb. So the clock states here labeled 1 and 2 are vibrational levels in the ground state. So here state 1 is the most weakly bound, while state 2 is deeply bound toward the bottom of the molecular potential. And these clock states are coupled by a coherent Raman transition, which is via this off-resonant intermediate excited state. The optical lattice frequency that's shown with the dashed yellow line is red detuned from that excited threshold. So let's focus on the relevant quantum states. In orange and blue are the upper and lower clock states, which have vibrational numbers 62 and 6, and no rotational angular momentum J. And moreover, the lattice is near resonance with a transition from state 2 to a deeply bound, long-lived rho vibrational state in the 1U excited potential. And this state, where the lattice is not resonant but near resonant with, is highlighted in green. So when the molecules are in an infrared lattice, the clock states are both downshifted in energy. And so the molecules, therefore, are optically trapped. And generally, these clock states will see different trap depths. And for this reason, the clock transition is light shifted and also broadened due to the thermal spread of the molecules. But when the lattice frequency is deliberately blue detuned from this green intermediate state, the AC Stark shift pulls the blue and the green states slightly closer together. And at a specific lattice frequency, this trap depth, which I call U, for clock state 2 exactly matches the trap depth for clock state 1. And this is the magic wavelength at which the clock resonance sharply narrows, since it's no longer limited by the inhomogeneous Stark broadening. One way to search for these magic wavelengths is to measure the clock shift, the shift of the clock transition versus the trapping light power. And to do this at various wavelengths that are shown here in different colors. And the wavelength with the zero slope is magic, which here is the red line. So as we sweep the lattice frequency through the narrow 1U resonance at green state, as we search for the exact magic frequency, we can directly measure the AC Stark shift of this deeply bound clock state 2. So here we change the lattice frequency from about 5 gigahertz below to 5 gigahertz above the resonance and see the dispersive Stark shift curve. The vertical green bar shows the lattice detuning where the polarizabilities of the two clock states are equal, and this corresponds to the magic frequency. And here is where we expect to see the narrowest clock resonance or the longest coherence time of the clock state superposition. And here we plot the clock resonance line width. So its baseline shows here a nearly 100 kilohertz width due to this lattice-induced broadening. And the line width further increases as we approach resonance. But at the magic frequency value on the blue side of the resonance, it drops quite dramatically, in fact, by over 3 orders of magnitude. And here are a couple of clock spectra on either side of the resonance, but both are away from the magic frequency. So here we see the expected light shift and broadening from the lattice lights that are both on the order of 100 kilohertz. But at the magic frequency, the resonance is symmetric and very narrow. So this is the zoomed in spectrum of the vibrational clock resonance at a magic lattice frequency. This resonance is 30 hertz wide, which is a 3,000-fold improvement over a non-magic lattice wavelength. The resonance frequency itself for this clock state pair is 25 terahertz. So this spectrum corresponds to the quality factor of 8 times 10 to the 11. And I'll note here that the intrinsic Q factor for this molecular clock is extremely high. So the performance will be determined only by technical limitations. And besides using the narrow width of the clock resonance to quantify the coherence of the clock states in the magic lattice, we can directly drive quantum Rabi oscillations between the clock states. So here, essentially, the molecule is made to oscillate between its tightly bound state and its weakly bound state that has a long bond length. And a well-chosen magic frequency helps us reach very long coherence times for the molecular clock. Here is the Rabi oscillation between the molecules in different vibrational states that are separated by nearly 30 terahertz. The oscillation decays with a long time constant of over 100 milliseconds. So we're not yet limited by the two-body collisional lifetime of the molecules. That's shown here with purple triangles for the upper clock state. But instead, we are currently limited by the lattice-induced loss of molecules in the lower clock state. That's shown with the red squares, which we are trying to understand and mitigate in order to extend the lifetime even further. So our current implementation of the molecular clock is already precise enough to start providing useful results, at least for the dimers of the dominant strontium-88 isotope. The top data sets is a fairly coarse and preliminary scan of the ground state van der Waals potential, showing all 63 vibrational states. The bottom plot shows the differences between these measured binding energies and the theoretical energies that are derived from partly from prior measurements. So this data was collected in our lab using 2-photon Adler-Towne spectroscopy, where even the initial precision for some selected states, shown with the red points on the lower plot, is more than 4 orders of magnitude higher than in previous work that uses classical spectroscopy. So in general, a molecular clock that provides very precise measurements of the vibrational state is an excellent sensor of the interatomic force. So when the positions of the bound states are known with an uncertainty below a part per trillion, then the interatomic potential and the binding force that holds the molecule together can be reconstructed with that similar precision. And this is, of course, in addition to other exciting applications of molecular clocks, such as metrology in the terahertz regime and measurements of the temporal stability of the electron to proton mass ratio. So as I mentioned just now, high precision interatomic force sensing can lead to discoveries of new physical forces. For example, it could be possible to use molecular clocks to learn about gravity at the ultra short range. For example, our strontium molecules can be pictured as pairs of atoms that are separated by their bond length, which can vary from about 0.5 to 5 nanometers. And this bond length is set mostly by electromagnetic interactions between all the electrons and nuclei in the molecule. Since the nuclei are relatively heavy, Newtonian gravity also contributes to the binding potential and makes a very tiny correction to the bond. Any possible deviations from Newtonian gravity can be parameterized, for example, using the exponential Yukawa term presented here with a magnitude A and length scale lambda. From previous experiments that use various quasi-classical methods, we know that at this nanometer scale, the magnitude A is smaller than 10 to the power of 22, which is, of course, a huge number. So in other words, there could be a huge correction to regular gravity, and it wouldn't contradict any experiments that have looked at interactions between spinless masses. And the molecular clock that we are working on is a fully quantum system that has the potential to go to higher sensitivities. Okay, to summarize, we have created samples of ultracold van der Waals molecules in their absolute ground state. We use these molecules to demonstrate a vibrational molecular lattice clock. And this clock now achieves a quality factor of approximately 10 to the 12 and coherence time of 100 milliseconds across the molecular potential depth, with still a lot of potential for improvement. This clock was actually first proposed some years ago for measurements of slow time variations of the electron to proton mass ratio, or mu dot, But we are also excited about its applications to these sub-part per trillion interatomic force measurement and potential search for new mass-dependent forces. And in conclusion, I would like to thank my collaborators, especially the graduate students who work very hard on these experiments. In particular, Con and Emily contributed to the molecular clock project. We are also very grateful to our theory colleagues, Robert Mashinsky and his student, Ivana Majewska from the University of Warsaw in the chemistry department. And thank you very much for your attention.
Thank you, Tanya. It was extremely interesting to learn all about these optical clocks with molecules. And so we have a couple of minutes for questions. I maybe would start. And so I have not worked with molecules, though. I'm just curious, how many molecules do you get per your lattice pancake?
Okay, so we have about 5,000 to 10,000 molecules total, and something on the order of 100 pancakes. So in the order of 100 molecules per pancake, maybe to start with, but that's a lot. So they actually start, when they collide strontium-2 and strontium-2, they can form a trimer and an atom, and then they leave the trap. So pretty quickly it gets down to maybe from 100 to 10 molecules or a few molecules, and then they decay more slowly. So basically 100 pancakes with maybe 10 molecules each.
Mm-hmm. So this is the main basically limiting, so the main issue limiting the coherence and the kind of decay time for the molecule.
Right. So yes, that would definitely limit it to about 100 or to a couple of 100 milliseconds. That's a solvable issue because we can impose a lattice from the remaining two directions, and then they would be, instead of in pancakes, they would be in kind of individual spots, and they would be blocked from colliding. So that we could solve using that approach. But now that we are limited by something that's a little bit faster than that, and that depends on the lattice intensity. So the stronger the lattice, the faster our loss, which makes sense because the lattice is used to make the magic wavelength by basically talking to one of the clock states and tuning its polarizability. So it also scatters from that state. It's just there's a bit of a mystery because it scatters more than it should. So that's what we are trying to solve. Once that's solved, then we'll be at the collisional limit, and we can solve that by putting the molecules into a three-dimensional lattice instead of pancakes.
And can you trap initially the less number of molecules, or it's not up to control right now?
Yeah, we can trap less, and then, but I think we probably don't get, in the net signal to noise ratio, we probably don't gain from that. We probably would gain by just separating them into their individual sub-traps.
I see. Great, thank you a lot. And I suggest we continue this discussion in our roundtables, and people who have questions or who maybe did not manage to write them on time, please join us there at the end of this session.